Okay, so this is 2007, step 2, question 3, which is quite a nice question actually. It actually teaches you good integration technique and practices. I like these type of questions. I really like the step questions where it actually teaches you a brilliant technique in mathematics, and they give you parts and guide you through it. So it's really nice, right? Well, some of the step questions are brute force, which I don't like in general, but this is one of them, which really teaches you good lessons. All right, so by writing x equals to a tan theta, show that for a not 0, the integral 1 over a squared plus x squared equals to 1 over a arctan x over a plus a constant. Okay, that's just standard A-level book work, right? And it's in a formula book, right? So if you're the type of person who always looks at the formula book, then this question might be helpful for you to understand why the formula exists. Yeah. I think this is pretty straightforward. I'm just gonna give you some sketches. Dx equals to what? Like a sec squared theta d theta. Well, then you sort of sub this in. Then you have 1 over a squared plus a squared tan squared theta over what? Sec squared theta. A sec squared theta. Sorry about that. And what have I got? I've got d theta at the end. Yeah, and etc. Really. I can't be asked to write the rest. Right, you know how to do it. This tan squared plus 1 becomes sec squared. Cancels with that. Well, you need to compensate here, right? So you need to pull 1 over a out. That's where the 1 over a here comes from. Right, and so on. Right, if you're doing a step exam, you know how to do these things. Okay, and obviously, after you integrate, in terms of theta, then you need to sub back in for x, right? Because the function was, the integral was in terms of x. Okay, cool. What next then? Part 1. Let I equals to, from 0 to the power of 2, cosine over 1 plus sine squared. Evaluate I. Okay, again, think about why this part exists, right? Why does the top exist? Why does it exist? Well, that's because you're supposed to make it into that form and use that, right? Okay, what's a sensible substitution to do then? Well, I want to get rid of this sin x, right? Because in here, in the form here, this was x squared. There was no sign involved. Yeah, so I want to get rid of it. Okay, so, well, let's go u equals to sine x, right? Just get rid of it. Well, then what have I got? du equals to cos x dx, right? Beautiful. Cos x dx. That goes away. Right, so this becomes what? Well, the limits you could change yourself. I don't know what they are. Well, okay, it's sort of obvious. Let me write it down there. 0 to 1. And what I've got? 1 over 1 plus u squared du. Standard integral, right? Arctan, etc. Alright, and you have limits. Chuck in the limits, right? You don't even have to sub back in for x. Easy. Okay, I'm not going to do that then. So, part B. Use the substitution t equals to tan half x to show that from 0 to 1, 1 minus t squared over 1 plus 6t squared plus t to the 4 dt equals to a half I. Okay, to be fair, if they didn't give the t equals to tan a half x substitution, this might be a really tricky integral to evaluate, right? So that's why they told you this. Well, to be fair, it's actually quite a famous substitution. It's I think it's in the A-level third appear books. The optional modules for EdXL. For other exam boards, I'm not sure, but this is a really famous substitution. Okay, so t equals to tan half x. So what can we do? Well, do what we were told. So dt equals to what? dt equals to sec squared half x, or times a half, I suppose. So and dx, right? Something along these lines, okay? And what have we got? So I have something like from 0 to 1. Doesn't matter. What have I got then? So, okay, the bounds you change yourself, okay? I don't know what the bounds are. 1 minus, what is t again? Oh yes, tan squared half x over what? Over 1 plus 6 tan squared half x plus tan to the 4 half x. And what is dt? dt is just a half sec squared a half x dx. Okay, well then I think what remains is just a brute force sort of thing, right? There's nothing special at this point. Then the next thing is that, okay, the boundaries I'm not going to write. So let's multiply top and bottom by what is it? A cosine squared, let's say. Okay, so the top becomes what? Cosine squared half x plus minus sine squared half x over what? Over cosine squared half x plus 6 sine squared half x plus, well, this is slightly annoying, so I have sine to the 4 half x over cosine squared half x. Okay, so I still have 2 more cosines to get rid of. Let's take the half in front, okay? Let's take half in front, because the question wanted a half I, right? So, it's sensible to take the half in front. Okay, and so sec squared, if I put it in the denominator, this is cosine squared half x dx. Okay, hopefully all good is here. Just algebra, basically. Okay, now let's do it. So this becomes a half. So cosine squared half x minus sine squared half x. Now, think about what this is when I'm doing the thing. Okay, think about what that sort of looks like. Now I have cosine to the 4, 1 over 2x, plus 6 sine squared cosine squared. Now I can't be asked to write the half x. It's really annoying. Okay, so I'm just going to leave it for now. Sine to the 4. All right, that's inconsistent notation, but you get the idea, right? I'm just trying to show you how the question is sort of done in a skeleton. Okay, so what's the top? The top is the double angle formula for cosine. Right? So this is a cosine x over what? Over what? This is cosine squared a half x plus sine squared a half x all squared plus how many? Plus 4 lots of sine squared cosine squared. Okay. Then what happens? What is this? This is just 1. Beautiful. Cosine x equals 1 plus what? What is this? Use the double angle formula for sine. What is it? Sine squared x. And what is this? This is just I itself, right? This is just I itself. That's why it's half I. Alright? Now, the algebra is not as tricky as you think. Right? Just sines and cosines. And writing order tangents in terms of sines and cosines is always a very sensible thing to do whenever you're treating, trigonometric expressions. Right? Because I only want to deal with 2 things instead of 3, right? When I could deal with 2 things only, why give myself a third thing to look at? Yeah? So I would always change it to sines and cosines. ASAP, right? You see, the first step, straight away. The next step has no tangents in it. Yeah? And by the way, like sec squares, I hate these things. Just put the cosine in the denominator. Right? Just deal with cosines and sines themselves. Okay, helps with life. Alright, now, part 2, evaluate from 0 to 1, now the 6 becomes 14. Classic step question, right? They show you how to do the easy one, and then they want you to do the hard one without giving you the substitution, right? This is a classic step. And that's how you are trained to become a better mathematician as well, I suppose. Okay, so 14t squared. Let's actually observe what's happening. So, remember in this integral here, when we got to this step, we had this 4 sine cosine. We had this 4 sine cosine thing. Okay, so let's think about what happens when I have 14 instead of 6. Well, all the steps above are sort of equivalent, but only this 4 becomes 12. This 4 becomes 12. So, what's the significance of that? So, this is multiplied by 3, right? Multiplied by 3. Okay, if this thing is multiplied by 3, this is something squared, right? Remember, this is something squared. If this something squared is multiplied by 3, that means that our substitution has to do what? Has to multiply by root 3. Right? Because I need it to be squared. Then I could get the 3 that I desire. Yeah? So here, the substitution is just what? T equals to root 3 tan half x. That's how you see the new substitution, right? Because basically every step is just the same. Just the 6 here becomes 14. I mean, I don't care. 6 becomes 14. Fine. Okay. I don't mind. Right? And etc. Right? And then obviously you have to adjust for the constants and so on because I put a root 3 in front. So probably this has a root 3 here, it's probably root 3 over 2, etc. Right? This is probably root 3 over 2 all the way. Okay, this is getting really messy, but you get the idea. Right? This becomes 14. And the beautiful thing is, look, so this becomes what? This becomes root 3, this becomes 3 plus 3 sine squared x. That is why we chose root 3 as a substitution, right? Because in front here, now I could get the 3. Then what could I do? Okay, this is root 3 over 2, by the way. Then what could I do? I could take the 3 out. That's what? 1 over 2 root 3 times I, isn't it? Yeah, okay, maybe I made some mistakes with the constants somewhere, right? But it doesn't matter. That's the main idea, right? That's how you choose a substitution, by observing what you're doing in the steps, by actually understanding what is happening inside the integral. Okay, this is a really good question, I think. It actually teaches you good calculus and good habits. Yeah. Okay, cool. So that's about it. All right, there are lots of good calculus questions in STEP. So this is one of them. Okay, so you should always choose these things in the exam. All right, these are really good questions.